Today, we want to talk about finding antiderivatives. Recall that this is connected to the fundamental theorem of calculus of both parts. We have the first part where the definite integral from a to b of f prime of x dx is f at b minus f at a. So we're evaluating a definite integral using an antiderivative. In this case, since f prime is the derivative of f, f is the antiderivative of f prime. The second part says we can do this in the other direction as well. We can construct an antiderivative using the definite integral. This is really useful because definite integrals are just area. We can approximate definite integrals by approximating area, and we can do this as long as we have a continuous function to any degree of accuracy that we want. So we need the second part because not all functions have what I called nice antiderivatives. That is, finite combinations of elementary functions. So we always have the ability to construct an antiderivative using a definite integral, and that's super useful. We still want to build up the skill of finding antiderivatives. All right. I suppose someday I should justify the building of the skill of finding antiderivatives, but it is not today. So let's find some antiderivatives. Remember that all of our information about derivatives is now a piece of information about antiderivatives. So recall last week, derivative facts are now also antiderivative facts. So we spent last week turning our derivative facts into antiderivative or indefinite integral facts. What I mean is that if we know that the derivative with respect to x of x to the n is nx to the n minus 1, we just invert this process to find the antiderivative or the indefinite integral, so that the integral of x to the n is x to the n plus 1 divided by n plus 1. And then, we have to put a plus c, that's the constant of integration. So our derivative fact became an antiderivative fact. And we should also note that this is for n not negative 1. So this only works as long as n is not negative 1, because we don't want to divide by 0. What's happening is we're just turning our derivative statement around. The derivative of x to the n is nx to the n minus 1. So in the intermediary, as an intermediary, we could say the integral of nx to the n minus 1 dx is plain old x to the n plus some constant. So the antiderivative has an exponent that's 1 higher than we started with, and we divide by that new exponent. That's why the n disappeared when we integrated. So we spent a lot of time taking our derivative facts and turning them around to antiderivative facts. What we want to do now is add to that list. We want to look at some of the more complicated derivative rules and try turning those around. So, for example, So recall we had a chain rule which said the following: the derivative of a composition of functions, f of g of x, is the derivative of f with respect to g times the derivative of g with respect to x. So here's the chain rule. We take the derivative of f with respect to g and multiply by the derivative of g with respect to x. And then we imagine that the dg's cancel out and just end up with df dx. So since this is a fact that we have about derivatives, we can turn it around and make it a fact about antiderivatives. And that just means if we integrate the left side, we end up at the right side. So the integral of f prime of g of x times g prime of x dx is f of g of x. And then since we're integrating, plus some constant. So here we are just turning around the chain rule. When we turn around the chain rule like this, we call this process integration by substitution. Integration by substitution is the anti-chain rule. So integration by substitution undoes the chain rule. Let's look at an example of the chain rule and then see how that would show up in an integral. If we wanted to find, let's say, the derivative with respect to x of the square roots of x cubed plus 1. So what we have is an inside function. We've got this x cubed plus 1 inside an x to the 1/2 power. So our inside function is an x cubed plus 1. And then the outside function, oh, I used f and g, so that's our g of x. Then our outside function, f of x, would be the square root. Well, the inside is u. Can't quite remember back in the chain rule days what notation I was writing. So the outside function, f of g, is the square root of g. Because I can't remember if I was using y, u, and x, or f, g, and x. That's okay. So To find the derivative of the square root of x cubed plus 1, we take the derivative of the outside with respect to the inside. The derivative of 1/2 of g is of the derivative of the square root of g. We can read this as g to the 1/2 power. So the derivative of something to the 1/2 power is 1/2 of that thing to the minus 1/2 power times the derivative of the inside. So we have 1/2 of x cubed plus 1 to the negative 1/2 multiplied by the derivative of the inside. So if g of x is x cubed plus 1, g prime of x is 3x squared. So we multiply by 3x squared. That's just utilizing the chain rule to take the derivative. We could clean this up. We could write this as, say, 3x squared over 2 times the square root of x cubed plus 1. Maybe pull the 3/2 as a coefficient. I don't know. At this point, we're in the style game. Might be good to write this since we were given a function with square roots, so our answer maybe should include square roots. You can also just write 3/2 x squared times x cubed plus 1 to the negative 1/2. The important thing is that we use the chain rule to find the derivative. All the derivatives that we know are now also going to be antiderivatives that we know. So this means that if we integrate 3x squared over 2 times the square root of x cubed plus 1 dx, we'll go back to what we started with. This will be the square root of x cubed plus 1 plus some constants. We want to remember that any constant factors are just going to end up being constant factors that we can multiply and divide by constant factors. So for example, for example, we have the integral of just x squared over 2 times the square root of x cubed plus 1 dx. If we divide what we start with by 3, we divide what we end with by 3. Plus c is an arbitrary constant of integration. If you divide an arbitrary constant by 3, you just have some other arbitrary constant. The constants of integration are like George Foreman's kids. They're all George. Just put a plus c at the end. We only have to worry about it if there's going to be another integration afterwards.
Hey, Professor, quick question. How did you get the 1 over, like 1/3?
So notice that I just took what I started with here and I divided by 3. If I multiply this by 1/3, I'll multiply this side by 1/3 as well. So the integral of 3x squared is x cubed. the integral of x cubed is 1/3 x cubed. Excuse me. If the 2 isn't there, let's put another layer on. If there's no 2 in the denominator, 2 is still just a constant factor. If we're integrating x squared over the square root of x cubed plus 1 to x, then we're missing the 3, so we'll have a 1/3, and we're missing a 2 in the denominator. It's like multiplying the first one by 2. So that would be like taking this first one and multiplying, actually taking the second one and multiply both sides by 2. What we're trying to see is that constant factors just get carried along. So we can check if we take the derivative of, let's say, 2/3 square roots of x cubed plus 1, we should get back to x squared over the square roots of x cubed plus 1. So let's check. So the derivative of 2/3 x cubed plus 1 to the 1/2 is going to be 2/3 times the derivative of the square root of something is 1/2 that thing to the negative 1/2 times the derivative of the inside, which is still 3x squared. Now we can see that the 2's will cancel out. That 1/2, the 2 will cancel out with the 1/2. That 1/2 showed up because we took the derivative of the square root of something. And then the 3 from the 3x squared will cancel out the 3 from in the denominator. And we'll be left with just x squared over the square roots of x cubed plus 1. So everything checks out. If we differentiate, we get back to where we started. When we're using the chain rule to find derivatives, we have to remember to multiply by the derivative of the inside. When we're using the chain rule to find derivatives, we need to remember to multiply by the derivative of the inside. When using the chain rule to find derivatives, remember to multiply by the derivative of the inside. When we start going the other way, when we use integration by substitution to find antiderivatives, we need to look for the derivative of the inside. We have to look for the derivative of the inside that showed up because of the chain rule. So let's look at another example. So let's suppose that we want to find the derivative of the sine of x cubed plus 1. In this case, our inside function is the x cubed plus 1 again. G of x is x cubed plus 1. The derivative of the inside, g prime of x, will be 3x squared. And then our outside function will be sine of g. So using the chain rule, we find the derivative of f with respect to g. The derivative of sine of something is cosine of that thing. Times the derivative of that thing. We don't like writing our polynomials last. We want to write our polynomials first. So we would probably write this as 3x squared times the cosine of x cubed plus 1. We had to remember to multiply by the derivative of the inside. If we turn this around to an integration, we can see all the parts. We've got the integral of x squared times cosine of x cubed plus 1. So we can see that x cubed plus 1, that's going to be our inside function, and it's inside a cosine. That x squared out in front, that's the derivative of the inside that we're looking for. Once we see that derivative of the inside, once we see that there's that derivative of the inside, that tells us that this derivative was found using the chain rule. And so that means that we should use substitution to undo it. In this case, notice I've dropped the 3, but the 3 is a constant factor, so no worries there. We'll just have a 1/3 sine of x cubed plus 1. Integrating, so we'll make sure to put plus c. So what we're doing in this process is we're saying that x cubed plus 1, we're still making the same kind of identifications that we did for the chain rule. We're saying the inside g is x cubed plus 1. And this x squared is g prime of x. Well, x squared is not exactly g prime of x because g prime of x is 3x squared. But we're only off by a constant factor. So 1/3 of g prime of x is equal to x squared. And then that's where that 1/3 comes from in our antiderivative. So these are the things that we're looking for. We're looking for the derivative of the inside so that we can use substitution. That derivative of the inside is what makes substitution go. For example, we know that the derivative of, let's say, e to the minus x squared, in this case, our inside function, is minus x squared, and it's sitting in an outside function of e to the x. When we're finding a derivative using the chain rule, we need to multiply by the derivative of the inside. So the derivative of e to the minus x squared is e to the minus x squared times the derivative of the minus x squared, which is negative 2x. We wouldn't want to write it this way. We had to use parentheses. If we forget to use the parentheses and we just put a dot, then the dot doesn't show up, and I think you're trying to tell me two terms. So let's just write this in a better order. Let's write minus 2x e to the minus x squared. This means that if we're going to integrate minus 2x e to the minus x squared, we should get back to e to the minus x squared. So the integral of x e to the minus x squared dx, since I've dropped off a factor of negative 2, I'm going to have to multiply both sides by a negative 1/2. Let's see where that negative 1/2 comes from. So when we look at integrating x e to the minus x squared dx, we want to look for something that we can identify as the inside function. And that is still this minus x squared. And the derivative of the inside function, g prime, is minus 2x. We look at the piece that we have and it's just x, but minus 2 is just a constant factor. So I can multiply by a negative 1/2. Negative 1/2 g prime of x is x. And that's what we were looking for. So that x is just there to be the derivative of the inside. That's what makes this substitution work. And so that was the end of the sentence. I didn't inflect it correctly. That's what makes substitution work. Just fix that in post, even though my videos don't go through post. Imagine if when you were watching a movie, you couldn't watch an edited version. You just had to watch every single take of every single scene. Some directors are known for just doing like one take and go, we got it. I think Clint Eastwood is like that. Other directors are like, well, no, let's try it again. And they just do scenes over and over and over again. So we're looking for the derivative of the inside to make substitution work. The derivative of the inside is the factor that makes substitution work. So, for example, if we wanted to try to integrate, let's say, just e to the minus x squared dx, I can't do a substitution of minus x squared because I don't have a factor of, I don't have a constant multiple of negative 2x to be the derivative of the inside. So this is not substitution. Our inside function we don't have a factor of x to be the derivative of the inside. In this case, this integral is not substitution because we don't have a factor of x to be the derivative of the inside. So substitution is off the table for this integral. The previous example was not substitution because we didn't have enough. Now, this example is not substitution because we have too much. We've got two factors of x, only one of which can be the derivative of the inside. So this is also not a substitution problem. We have too many factors of x. I need one factor of x to be the derivative of the inside. But we don't have anything to do with, but we don't know what to do with the other factor of x. But there's another factor of x that we don't have anything to do with. We can't just have some spare factor of x that we can ignore. If we want our substitution to be x squared, we need one factor of x to be the derivative of the inside. Here we have two factors of x, and that's too many. That'll leave an x left over. So this is not a substitution problem. So when we decide what we want to be the inside, we have to look for the derivative of the inside as a factor in the integral to make substitution work. If we don't have that, then we have to do something else, but it will not be substitution. This seems like substitution would be super limited, but it is not. It is going to be our most versatile technique for finding antiderivatives. Turns out, even with this seemingly strict restriction, substitution is still our best move. It's one of our three best moves, not just in this application of integration, but math. Our three best moves, algebraically anyway, are to add 0, multiply by 1, or change your variables. Substitution is a form of change your variables. Any questions? One of my favorite things in this particular section, when you start reading integration by substitution, they lead with what they call the guess and check method. And I'm not sure that guess and check really qualifies as a method. I mean, it's clearly a method for doing things, but is it really something that that you would call a method for doing things? It seems kind of crazy that should be like some method. I mean, it is best. Guess and check is best when you're well trained and you have good instincts about what to guess on. In your mathematical career, think back to factoring polynomials. The fastest way to factor polynomials is to be really good at factoring polynomials, so you don't have to do any method. You just see what the factors are. So you're kind of doing a guess and check method. If your guess and check method is just to try every possible combination, that's going to be horribly inefficient. Imagine someone trying to open up a combination lock. If you don't know anything, you could just try every possible combination. There are going to be too many. But if you know what to listen for, you're kind of guessing and checking, because you're just spinning it until you hear the click. So that actually qualifies, I think, as a method. Then just like all 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, 1, 1, 5. That would be horrible. If someone starts doing that, it's probably faster to just hop in the car, drive to Home Depot, purchase a pair of bolt cutters, come back and cut the lock off. You know what I mean? In a later calculus class, I've taught a class called differential equations out of a couple of different books. And this was when I was teaching it in a very old style, which is very learn a bunch of techniques for doing things. And in one book, when I learned it, there was a method called the method of undetermined coefficients. And then when I started teaching it, I was using a different book, and it just called it judicious guessing. And I thought that was pretty dope, because what's the only thing we ever do? We just guess and try stuff. And when we learn a method, that's the result of taking the advice from someone who'd done a bunch of guessing before and said, no, don't just guess, do this instead. Learning from the people that came before. Because just starting off guess and check like every single time, that's a horrible idea. Which of these plants are poisonous? Let's guess and check. I'd rather have someone say, no. A couple years ago, Bob ate one of those and he ain't here no more. So let's not eat that one. Let's learn from Bob. Bob guessed and checked and said that one is not a plant that we should eat. You know what I mean?
Professor, another question. How come the last example on this page does not count as a substitution?
So the last example, we would want to make g of x equal to negative x squared, right? The negative x squared. But that means that for g prime of x, to make substitution go, I need to have as a factor a g prime of x, which is negative 2x. Now the negative 2 is not a concern, but I need the x, and I have too many of them here. I've got 1x can be the derivative of the inside, but I've got this other factor of x we don't know what to do with, or we don't have anything we can do. So
So you're
one of the
saying that it has
factors
to
of x,
match, right?
it's got to match. I need one factor of x. So if, for example, I had, so if, for example, I'm trying to integrate a square roots of x cubed plus 1, if I have a factor of x squared, substitution. That x squared is the derivative of the inside. It's off by a factor of 3, but that's a constant factor, so it's fine. So this is a substitution. But if we have the square root of x cubed plus 1, and we only have an x out here, that's not substitution. I need an x squared. An x cubed inside means that g prime of x needs to be an x squared. So an x on the outside is not substitution. I need x squared, but only have x. If we go the other way with it, no, that's a bad direction to go. I mean, it's the right direction, but I didn't go far enough. It's a mess. My dog was reminding me that x to the 5th is problematic as well. So here we have also not substitution. I need x squared. I have too many of them. I got x to the 6th. What am I going to do with that extra x to the 4th? So this is also not substitution. Need x squared. So I have x squared, but what are we going to do? So that's good. But what are we going to do with the other x to the 4th? That's where the problem is. So that's why this is not going to be substitution. Any questions? I see the message RIP Bob. Don't worry, this was a D&D campaign and the characters were 5th level. The cleric had Revivify and they had just scored a bunch of diamonds. Unfortunately, they forgot to neutralize the poison before casting Revivify. But fortunately, the cleric had 2 3rd level spells left. They cast Neutralize Poison, then Revivify, and then all was well. So Bob is fine. Especially since we weren't, except a little bit not so fine because we weren't totally sure that the cleric didn't do that on purpose. It was a cleric of the trickery domain, and he might have raised him to watch him die of being poisoned again. So I don't know. Sometimes players are cruel to each other. All right. That's going to do it for today. I will see you all on tomorrow, and we'll find some more antiderivatives. It'll be super fun. Everybody have a good day, and thanks for playing.